Good morning, everyone. I am excited to welcome you to today's presentation. We will be exploring the fascinating topic of memory management in operating systems. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. Over the next few minutes, we will cover the fundamental concepts of how operating systems manage memory, the techniques involved, and why it's so critical for system performance. So, let's dive in and get started. Welcome to today's discussion on memory management. As you can see, memory management is a crucial function of an operating system. It's responsible for handling the allocation and deallocation of memory spaces, which basically means it decides how and when memory is assigned to different processes, and when that memory is freed up. This process is vital because it ensures the optimal utilization of the main memory, making sure that resources are used efficiently without waste. Additionally, memory management plays a key role in protecting processes from accessing each other's memory space. This safeguard is essential for maintaining system stability and security, preventing one process from interfering with another. Understanding these core functions helps us appreciate how operating systems keep everything running smoothly behind the scenes. Let's take a closer look at the objectives of memory management. First and foremost, it aims for the efficient utilization of memory resources. This means making the most out of the available memory to ensure smooth system performance. Next, it involves the allocation of memory to processes when they need it, ensuring that each process has the space it requires to run effectively. After a process completes, memory must be deallocated or freed up so it can be used by other processes. Protection and sharing are also key aspects. Memory needs to be protected from unauthorized access, but at the same time, certain parts can be shared between processes to enable collaboration and efficiency. Finally, memory management supports multitasking and virtual memory systems, which are crucial for running multiple applications simultaneously and extending the apparent amount of memory available beyond physical limits. All these objectives tie back to the overall goal of creating a robust, efficient, and secure environment for executing multiple processes smoothly. Let's take a closer look at the memory hierarchy. At the top, we have registers, which are extremely fast but also very small and costly. Moving down, we encounter cache, which is still quite fast and slightly larger. Next is main memory, or RAM, which is larger but slower compared to cache. Finally, we have secondary storage, like hard drives and SSDs, which are much larger and more affordable but significantly slower. An important point to remember is that faster memories tend to be smaller and more expensive. That's why computers are designed to keep the most frequently accessed data in the faster, smaller memories to boost overall performance. The operating system plays a crucial role here. It primarily manages the main memory, making sure that data and programs are loaded efficiently and that resources are allocated optimally. By managing memory efficiently, the system ensures quick access and smooth processing, which is essential for a responsive and effective computing experience. This hierarchy and management strategy are fundamental to understanding how computers achieve such high performance. Let's talk about contiguous memory allocation. In this method, each process is assigned a single contiguous block of memory. This means that the process's memory space is located in one continuous segment, which makes access straightforward and efficient. Now, there are two main types of this allocation strategy. First, we have fixed partitioning, where the memory is divided into fixed-sized partitions, regardless of the process size. This approach is simple but can lead to some inefficiencies. The second type is dynamic partitioning, where partitions are created dynamically based on the size of the processes. This offers more flexibility, but introduces its own challenges. Speaking of challenges, two major issues come up with contiguous memory allocation: internal fragmentation and external fragmentation. Internal fragmentation occurs when allocated memory may be slightly larger than the process needs, wasting space within the partition. External fragmentation, on the other hand, happens when free memory is divided into small, non-contiguous blocks, making it difficult to allocate larger processes even if total free space is sufficient. These issues are important to keep in mind as they directly impact the efficiency of memory utilization, which ties back to our overall theme of effective memory management strategies. Let's talk about paging, which is a key memory management technique. Paging involves dividing physical memory into fixed-size frames, which are like slots that can hold data. On the other hand, logical memory, the view that programs have, is divided into pages of the same size as these frames. This setup allows the operating system to efficiently manage memory by mapping each logical page to a physical frame through a page table. This mapping is crucial because it keeps track of where each part of a program is stored in physical memory. One of the biggest advantages of paging is that it eliminates external fragmentation, meaning memory can be allocated more flexibly without leaving unusable gaps. Overall, paging helps improve memory utilization and system performance by providing a structured way to manage memory dynamically and efficiently. Let's talk about segmentation. Essentially, memory is divided based on the logical divisions of a program, such as code, data, stack, and other components. This approach helps organize memory in a way that reflects how programs are structured. Each of these segments has a base and a limit register, which define where the segment starts and its size. This setup provides a logical view to the programmer, making it easier to understand and manage different parts of the program. However, it's important to note that this segmentation can sometimes lead to external fragmentation, where free memory becomes scattered and inefficient. Overall, segmentation is a key concept because it aligns memory organization with program structure, simplifying programming and management, even if it introduces some challenges like fragmentation. Let's talk about virtual memory. This is a technique that allows us to run processes even when they are not completely loaded into main memory. It's particularly useful when dealing with large applications or multiple programs at once. Virtual memory is typically implemented using methods like demand paging or segmentation, which help manage how data is brought into memory only when it's needed. Essentially, it uses secondary storage, like a disk, as an extension of the main memory, which means we can run more programs than what the physical RAM alone would allow. Now, what are the advantages of this approach? First, it significantly increases multiprogramming, allowing more processes to run concurrently without running out of actual memory. Second, it provides isolation and protection between processes, which is crucial for system stability and security. And third, it helps us make more efficient use of the physical memory we have, reducing waste and optimizing performance. So, in the context of overall system management, virtual memory is a key concept because it enhances flexibility and efficiency, enabling us to handle complex and multiple workloads seamlessly. Now, let's take a closer look at some common page replacement algorithms. These are the strategies that decide which page to remove from memory when a new page needs to be loaded. First up, we have FIFO, which stands for first in, first out. It's pretty straightforward. The oldest page in memory gets replaced first. Then there's LRU, or least recently used, which replaces the page that hasn't been used for the longest time, based on the idea that pages used recently are more likely to be used again soon. Next, we have the optimal page replacement algorithm, which is more theoretical but provides the best possible performance by always replacing the page that won't be needed for the longest time in the future. Finally, there's the clock algorithm, which is a practical approximation of LRU, using a circular list and a reference bit to keep track of page usage efficiently. These algorithms are crucial because they help us manage memory effectively, especially when dealing with limited resources, ensuring that we make smart decisions about which pages to keep or replace to optimize overall system performance. Let's talk about fragmentation and how we can address it. First, internal fragmentation occurs when we allocate a block of memory, but some space inside that block remains unused. This wasted space can add up over time, reducing overall efficiency. Then, there's external fragmentation, which happens when free memory is scattered in small, non-contiguous blocks across the system, making it difficult to find large enough chunks for new allocations. To combat these issues, several solutions have been developed. One approach is compaction, which involves shifting allocated memory blocks to create larger contiguous free spaces. While effective, it can be costly in terms of performance. Paging offers a different strategy. By dividing memory into fixed-size pages, we can manage free space more flexibly, reducing external fragmentation. And combining segmentation with paging allows for more organized and efficient memory management, especially when dealing with programs that require different-sized segments. Overall, understanding these types of fragmentation and their solutions is crucial for optimizing memory usage and ensuring our systems run smoothly. Now, let's talk about swapping. Swapping is essentially the process of moving processes back and forth between the main memory and the disk. This technique is really important because it allows us to run more processes than the physical memory alone could support. By swapping, we can bring in only the processes that need to be actively executed and store others temporarily on the disk. This way, we make more efficient use of the available memory, ensuring that the system remains responsive and capable of handling multiple tasks simultaneously. It's a key concept in managing system resources effectively, especially when dealing with limited physical memory. Let's wrap up with a quick summary. Memory management is absolutely vital for the efficiency of an operating system because it directly impacts how well resources are utilized. There are several key techniques we can use, such as contiguous allocation, paging, segmentation, and virtual memory, each with its own strengths for managing memory effectively. Implementing efficient algorithms in these techniques is crucial to ensure that resources are used optimally, avoiding wastage and bottlenecks. Proper management also helps prevent issues like fragmentation, which can waste space, and it ensures process protection, keeping different processes isolated and secure. Altogether, effective memory management is at the heart of a reliable and high-performing operating system, tying everything we've discussed together.